I just want to welcome you to Live from Behind the Walls. So before I hand you over to our host and moderator, Daniel Lucani, and all of our speakers, I just have a few things to take you through. So first of all, okay, interesting. I need to switch. Great. So first of all, this talk is being recorded and it will be posted online afterwards. So if you missed some of our previous events, you can watch the recordings at the bottom of the page where you registered for this event. And here's a path and a picture of where you can find the videos. So I would like to present the organizing team for this event. So Daniel Lucani, who's a professor here at the Department of Electrical and Computer Engineering. And as I said, he will act as your host and moderator and also timekeeper today. And Hugo Macedo, who works as a research assistant here at the department. And my name is Litte, and I'm the community manager of Orbit Lab, which is also a part of the department. And if you feel like it, it would be great if you would present yourselves to each other in the chat. I know we have quite a few international signups today, so it could be interesting to know where you're watching from. And just briefly, to those of you who are not familiar with Orbit Lab, I can tell you that we're a tech and innovation hub and an open community for anyone with an interest in digital technologies and entrepreneurship. And as I said, we're also part of the Department of Electrical and Computer Engineering here at Aarhus University. So if you want to know more, you're of course welcome to reach out. Finally, we do host a number of other events that you are very welcome to attend. So here's a couple of upcoming events that you can read more about on our social media, which you can see here. So with that, that's it from me. I'll now hand over this virtual stage to you, Daniel.
Thank you everyone for joining us at the Live from Behind the Walls. So this is, I believe, the 5th edition of it, and it's the second time that we've been running it with some of the members of my section here at the department. And just wanted to thank, of course, a number of people. First of all, Orbit Lab for helping to organize this event. And of course, we have a number of, let's say, funding institutions and projects that have made this possible, right? Part of it is, of course, the Paul Jensen Foundation and the Center for Digitalization here at Aarhus University. And of course, there's a number of funding agencies like the Danish Free Research Council, the Innovation Fund, and of course, a number of companies and European projects. And particularly today, there will be part of the focus on the IoTalentum project, which is as you will see later on, a Marie Curie international or European training network focused on a number of aspects of Internet of Things. So I will go back at the end of this on that. Part of the presenting group, it's not only from our team, let's say at the Network for Computing, Communications and Storage group, right, so NetX, but we do have several members that are either PhD students, postdocs, or master students doing or carrying out currently their master thesis. And this is just some of the members of our group at this point. And of course, the NetX group is focused on everything that is coming next in networking, computing, and storage technologies. We do have 2 members that are from the let's say, the section on software engineering led by Peter Gorm Larsen, and they will be also talking about subjects that are related to cyber physical systems and modeling and software design. And I can better show you in our next slide as part of the program, right? So if you see the different presentations, you see a certain pattern between them. So the first 3 of them are definitely focused on different levels of systems design with sort of a bit of compression ideas, right? So some of them for IoT, some of them more general for more general compression in systems, right, and in file systems. We then have let's say, some work focus on digital twins. That is Mirgita, and she's one of the members from Peter Gorm Larsen's group. Then we have a focus on a mixture of privacy and security aspects for the IoT, and we have a mixture there between using compression ideas to deliver privacy of your IoT data, as well as, let's say, more, focus on security and attacks on sensors by Zahra, right? So, at the end of the presentations, we will also have around 10-15 minutes where I would like to introduce you to this new project that we are running, which is the IoTalentum Marie Curie project. Tell you a little bit about its goals and its general structure, and how we are training the next generation of IoT researchers and engineers for the future. All right, so I hope everyone is clear more or less on what it is, and I will tell you more later on, but we have an upcoming event November 24th, and I will tell you more about it. It's not going to be it's going to be organized by the same team, just not but focus on other areas. And at the end of the presentations, I will introduce you to Alexandra Iosifidis, which will be the host for that next edition. So a few ground rules. So we will have each of the presenters, let's say, in our roster today, have a certain time. And if you see me sort of saying time to stop, please stop. Or if you see my screen as showing my video, please stop at that point so that we have time. If you see, it's very packed, so there's not a lot of time for questions directly to the presenters, let's say, at least not orally, but you are encouraged, of course, as an audience, to ask questions to the different presenters in the chat, and the presenters will be available actually to answer those questions and try to provide some feedback on their presentation. So presenters, be ready. Everyone else, be very free to ask questions about the different topics. A final comment for the presenters: please share your video camera when you're presenting. Otherwise, you can just have no camera. But while you're doing the presentation, make sure that you're able to share your camera so that we can see you as an audience. All right. So with nothing more to do, I would like to stop sharing the screen, and would like to invite Thomas Wolff and Daniel Knudsen to present some of the work that they've done as part of their master's studies. All right.
So Thomas and I are master's students right now, and we are writing a thesis where we are trying to extend an existing compression algorithm called generalized deduplication. And we want to show you some of the things that we've been tackling and how far we've come, and also some results of our progress so far. So the introduction, the agenda here. First, to understand what we're doing, we need to give a brief introduction to deduplication, which is the compression approach we are building on top on. And then we'll explain how generalized deduplication is extending deduplication. And finally, our approach, which we call dynamic generalized deduplication, how that differs from the generalized deduplication. Then we will show some results from our research and development project we made last semester. And then we'll also show some initial results from the master's thesis we're currently working on. Lastly, we'll show some future work or some challenges and ideas we are working on if we have the time. So what is deduplication? Deduplication on a very broad level is trying to, like any other compressor, exploit similarities in data. So if you look on the right side here, we might have a file consisting of a lot of bytes, so a 10 megabyte file. What we are then doing is we're chunking this file up into smaller chunks. And for every chunk, we create an ID based on the content of that chunk, which makes us able to then match other chunks and then assess whether they are equal. If we have two equal chunks, we can then just note down the ID and then map the ID to the chunk, thus only storing the ID whenever we have a match. And this is very helpful and a very good approach for data where we have a lot of similarities and chunks are mostly the same. So this is the idea behind it. And what we then get out of it on a broad level is this map with the IDs to chunks here in the bottom, and then a sequence of IDs. So if you want to decompress it, you would then map each ID in the sequence to the map in order to get the chunk back, and then you could get the original file from the map and sequence.
Yes, and then when you talk about generalized deduplication, it's basically that we're trying to get more matches, increasing the probability of finding matches by dividing our chunks into a base and a deviation. And that's because that we have an assumption, and especially when you're working with floats or integers and stuff, we assume that the most similar bytes are in the beginning. Otherwise, you can also do something that's called permutation, but we're not going to talk about that. And then we have the deviation. And because of that, we get fewer unique bases. And hence we have to store less in our maps. But we still have to store the deviation for each chunk. So there's a trade-off there. But it's showing great results. And instead of only having the map and IDs and in the sequence, it's also have the deviation, and then we have to store the metadata to make sure that we know the length of the base, because also the base gives the opportunity to exploit the less data you have from the base generation to do analytics. For instance, you have less memory you need to work on, and you also have better computation time. Yeah, and then we also try to exploit this for the GTG. Next slide. Thank you. So DTD is basically that we are trying to create more bases per chunk, because Daniel, he thought of last year that maybe we can get increased compression performance, but also we want to add the granularity and customization when we work on approximation analytics to see if we can get better results. We are at the moment in our thesis, we're going to work on some approximation analytics with some of the other PhD students. And what it gives us is that we hopefully get fewer bases when we try to create more bases per chunk, and hence need to store less. But that also is dependent on how the data are constructed and how many samples you got to compress. So instead of only having one map, you have a map for each unique base, for base 1 and base 2. And then you have to store the IDs for each base in the beta sequence with the deviation. And store in the metadata, you have to store both base lengths as well. Yeah.
Yes. So hopefully this makes sense that we are trying to extend the generalized deduplication where we only have one split of base to deviation, but now having two bases. And then from running and testing this out from our research and development project, we tried to do it. Oh, sorry, this is your slide.
Yeah,
My bad.
that's
Go
all
on.
right. Yeah, and in our research and development project, we looked at ECG data set, which was actually very small, and hence it was actually quite tough to make sure that we got enough compression gain. But when we compared it to deduplication and GD, we actually got the same compressions roughly with generalized deduplication, and we found out that the most cost expensive part of our storing part when we have multiple bases is the ID representation length. So we found out that we could use Huffman for further compression of the ID representation to the chunks, and then outperformed actually GD. And GD also got better when you used Huffman, but not in the same degree. So then GD was actually better. And we actually used this to, confirm that this was an interesting topic to investigate. And that is what Daniel will talk about now for our thesis. And we only have 3 minutes, just so you know.
Yes, okay. So, like Thomas said, the initial results on this one data set seemed like maybe there's something interesting to investigate here. So what we set out to do was to bring it maybe to a bigger data set with, in practice, what we've done is having 4 variables in a data set, each containing 32 bits. And then we have 5 different sizes of data set to see how our approaches compare on different sizes of data sets. And what we found out was that our approach is actually achieving a higher compression rate compared to both GD and deduplication. And it also allows for some more analytics capabilities because now we have 2 bases and you can do analytics on only one base or include them both, and you can customize it. And to quickly show you what this looks like is here a plot where you can see on the right side a compression ratio, which is very bad right now because it's more than 1. So you're basically using more storage than just saving the data set itself. On the left side, we have here 10 is 10,000 samples, 100,000, 200, 400, and 50,000. And what I've shown now is having the length of base 1 being all the bits we have in each chunk. This is basically deduplication. But if we allow for a deviation to, the algorithm to have a deviation, which is then generalized deduplication, we can see that we now get some results here where we actually get a compression ratio below 1. So already we can see by having a deviation and a base, we get some nice configurations here where the length of base 1 is between 55 and 35 bits and the deviation rather large. And now what we then found out was if we then allowed for a base 2 to also exist, we were able to get results of a compression ratio all the way down to 0.55 across different data sets. And these are the specific configurations of each base. So this allows for more compression on our data set and also allows for more analytics capabilities on the bases because you can do some initial analytics only on base 1 and not care about base 2 and deviation, and thus getting some initial results on your large data sets with less compute and less resources. And that's the gist of it. I don't think we have time for future work. It's basically just what about 3 or 4 bases and outlier detection and stuff like that. But yeah, that's for later, I guess.
Yes. Thank you, guys.
Yeah.
All right. So I think our next speaker will be Alexander, I believe.
Cool. So I'm just like Daniel and Thomas. I'm currently writing my master thesis, and I started on the project as an R&D project in the spring this year. So what I'm going to talk about is distribution of data according to ratio usage. So that basically means that I'm trying to figure out how to distribute data. So when some data becomes more popular, I'll try to move it onto more servers to actually handle the load of that given file. And that's what I'm going to present now. So first, the agenda. The agenda is that I'll present the motivation, then I'll try to describe the system I built, and then the implementation and how I did the measurements during the research and development project and the results. And if I have more time, I'll show or just talk briefly about what my master thesis is about. So first, the motivation and objective of this project was because in the world now we store a lot of data, and we keep storing more and more data, especially with all the IoT data that people are starting to collect. As well, now that people are getting accustomed to having stable internet connections and stuff, we also want reliable access to all our data, and we want to, when we request it, we want it and not wait or getting some weird errors. So also being able to always get the data we want. So the objective was to investigate how to distribute data for reliable access and minimize the amount of stored data. So first, to describe the system. So in the beginning, we had 3 different ideas of how to building a system. So it was basically 2 really simple ideas about how to distribute the data, and then we came up with an idea where we are using thresholds to actually know how much data we put on each server. So we called it the percentage system, where we basically say is that a server should only hold around 80%, for example, of its maximum capacity. In regards to when people request the system, we don't really think much about how much data each server could hold. It was more about the amount of requests that people put into the system. So that also means that we have these performance metrics, which were about how many requests we actually dropped. So that was kind of our main uh, performance metrics. And then the other one we looked at was the network traffic, because we know that network will be a bottleneck, and therefore we looked at, for example, how many files are we actually moving between the servers in the system. So to simulate the system shortly, we will just have a lot of users here, and then we have the system that kind of delegates where the files are located. And we can see here that one server has a lot of files, while 2 others might have less files, like server 2 and 3. And these servers might then have a lot more requests for, let's say, the green file we see here, or the blue file, or something similar. So just to shortly go into how we did the implementation and the measurement of this, it became a simulation in Python because it's hard to simulate physically, also based on the amount of time I had in the research and development project. So basically what the system does instead is it loads in a CSV file where I have defined how many files there is, and then it runs, then the system loads it and distributes it to many simulated servers, uh, where it basically ran an algorithm that tried to figure out where to place the given files based on how we estimated that it would be a good idea to do. And we tried with different models to actually see how the system performed. We tried with a random one where it's basically just between, I think it was 0 and 200 requests that could come for a specific file in the given period, and then it changed for each period in the system. Where we have other models like Brownian motion and a custom Brownian motion, which basically was that the amount of requests coming in for a file were more fluent, and the custom Brownian motion just had some specific time frames where it then kind of spiked to actually test how the system worked. And the last model we had was something called a shot noise model, which is basically, it's not a random model, but it's basically just like a file does not have any request, and then suddenly it spikes a lot, and then it decreases quite rapidly again. And we can see later on in the results how the system actually handled these different things. And the measurement was stored in a JSON, which we then did a lot of visualization on. So this is actually the first visualization. This is just how to show how the system actually handled it. So this GIF shows that we have 5 files in the system. They are located on the right-hand side, and then we have a lot of servers on the left-hand side. So basically, this is a simulation where we get a lot of requests, and then the system scales up and starts scaling down again, where we can see that the amount of servers on the left-hand side here increases and decreases, and the numbers we see is just the amount of requests that each server handles. So when they handle few requests, then we start to scale down again. So to move on to the results, so when I did the final implementation and test for the system, we did it on a period of 1,000 ticks or periods. But to actually see what's going on in the system, I have zoomed in for the first 200 here in the first slide, where the blue here is kind of the amount of servers we have in the system, and the orange is that we are trying to provision more servers to actually try to react to how many requests we have. So we can see that the system scales up and down. While on the right-hand diagram here, we see other kind of data, but it's quite similar and looks similar to the left-hand side, but it shows the amount of requests that we could actually handle in the system, as well as the amount of requests that we dropped. And the area here, the gray area, shows how we scale up and down in the system. So when we go above the gray area, then we start to provision more servers, and if we go down, then we start to removing servers. And this is then just for 1,000 a period of 1,000 ticks up. And we can see that when we move along, the system gets a higher gap, which means that it actually is able to handle more and more requests based on that we have more servers that has a little wiggle room before they are maxed out to the max amount that they can handle. And that's also showed here. So we can see actually the beginning where we zoomed in that a lot of the requests that we dropped during the simulation is in the beginning when the system is scaling up to actually figuring out how much data that's currently in the system, and then it kind of flattens out and we don't drop much in the last part of the simulation. And the model we saw before was this Brownian motion, where the system performed really well. So this one is the shot noise ratio. And what this basically shows is that the system is probably not reactive enough for this kind of model, because a lot of requests are dropped. Because when we see the black here, that's the amount of requests, and the yellow is the amount of requests that we actually handle. Yeah. Yes, and here we can see some results about how much the system dropped according to how much it could handle. And on the right-hand side, it's how much it dropped based on the amount of requests. And for example, here we can see that the shot noise model actually drops a lot of requests, which we could see on the picture before. Yes, yeah. So right now I'm just trying to, in my master thesis, kind of build the system to actually test it in more real world than just a Python simulation. Yes, and yesterday I asked Daniel what he wanted me to do in the presentation, and he said he wanted fireworks. So here is some fireworks. Yes, that was it.
Fair enough. Thank you, Alexander. All right. I think now we have Lars Nielsen, which is one of our PhD students at the university, and Lars will be presenting some work on new file system that can perform generalized deduplication. So I will let him explain this.
So yeah, my name is Lars, and I'm going to present MinervaFS, a user space file system for generalized deduplication. It's a collaboration between myself and Daniel Lucani and researchers from the University of Neuchâtel in Switzerland. So as the previous presenters have addressed, we are seeing a higher amount of data that is being generated, and the velocity which the data is being generated, so the speed with which we generate data, is also increasing, and there's no sign of it slowing down at all. This is tied into both the rise of IoT, but also more and more people coming online, and we are finding more and more applications where we need to store data persistently. And it's estimated by 2025 that we will reach roughly 175 zettabytes of only publicly available data. So it's really important to note here, this number does not include any privately held data at all. And this, of course, puts an immense pressure on our storage systems. So we have to look at new ways of thinking about storage systems and also implementing new technologies, right? The current state of the art is, of course, to use compression algorithms that can be deflate, like the ones that, like the algorithm that is used in GZIP. Delta encoding, this is also called delta compression, classic deduplication, and then the technology that's already been described by our other presenters called generalized deduplication. So classic deduplication and how it differs from generalized deduplication, I'll just briefly discuss here. So in classic deduplication, you chunk the original data into smaller chunks, and you look for bit pattern repetitions. And in this case, let's say that all chunks that have the same color has the same bit pattern. So C4 is a duplicate of C1, but C2 and C3 has different colors. So we need to store C1 and C2 and C3 in our system, right? Now, this whole approach is actually quite costly because chunks can vary in size from a few kilobytes up to 100 kilobytes and even up to megabytes in size. And some systems even use chunks in the gigabyte range, right? So the way we handle this is we generate a fingerprint for each chunk, which is significantly smaller than the original chunk. And of course, unique for the chunk. And then we use this for comparison. So as an example, for instance, in MinervaFS, we use SHA-1, which creates a 20-byte hash. In ZFS, that is deduplication-based file system. They use SHA-256 and so on. So basically, it's just a way to reduce the processing time, right? Generalized deduplication is a bit different because we add a transformation step where we use a transformation function to generate the basis and deviation pairs from the chunks. And basically, it's, as also already stated, a way to increase the deduplication potential of a given system. So let's say in this case that the shape of the chunk describes the basis and the color of the chunk describes the deviation. So if we had just used deduplication here, it's clear to see that there would be no duplicates, but because we add the transformation, we get two bases that are the same, and these two bases are the same, and these two are the same. So we only need to store B1 and B2, and then we have to store the deviations as well. Right? So how did we actually structure MinervaFS? Well, MinervaFS is a fuse-based file system, so it resides in user space. This means that we don't need to add a kernel component or anything. So everything we are doing is basically in user space, except for the final storage of bases and metadata that is done in a kernel file system. In our case, ext4. So we have a chunking and transformation component, which generates our chunks and our deviations. And then we look for duplicates amongst the bases, and then we store the bases and deviations and other metadata for the files, right? We have tested MinervaFS with 3 different data sets. One is a satellite image data set with TIFF files. The other is actually the same data set, but pan sharpened. This is basically a way to make higher definition images. And as you can see, it does add 2 gigabytes more of data. And then we took some virtual disk images and basically just said like, okay, let's get something that is half a terabyte or a bit more, right? And the results we are seeing is actually quite cool. Compared to just like baseline ext4, we are able to provide 9.45% reduction and 9.17 for the pan-sharpened images. For the VDI files, we are able to provide 63.53 reduction. And this is actually the most important result, because if we look here where we just have ZFS with classic deduplication, we see there's no reduction. But where MinervaFS provides this 2.74 times deduplication ratio, right? Now, the reason for this is actually due to how ZFS stores metadata, and that actually eats up the gain from deduplication, which is actually there. Additionally, it's actually quite impressive that we're able to achieve this with MinervaFS, because even though gzip and xdelta, which is xdelta is an implementation of delta encoding, is better, we are still quite close to this, right? So that is pretty impressive. Another thing you'll also notice is that, and it's a bit difficult to see here, but ZFS with a compression first and then deduplication actually performs worse than ZFS just with compression and then MinervaFS. Now, the reason for this is actually the order of how ZFS does it, because ZFS does compression first and then deduplication, meaning that it actually damages the potential to find duplicates. So what MinervaFS do, and also SDFS, which is another deduplication-based file system, is that it does the deduplication first, and then we do the compression of the individual bases. And as we can see here, just like raw MinervaFS provides a damn good deduplication ratio. But if we go into MinervaFS with gzip, right, we see an even higher deduplication ratio, where ZFS far from as good with deduplication only, and even lower with both compression and deduplication. Now, one thing we should bear in mind here is that it is actually like still fairly good, right? The deduplication ratio achieved, but it could have been much better for ZFS potentially if they have swapped the processes, right? So essentially, adding compression does increase the deduplication ratio. And the reason we say it in this way for MinervaFS is because when we talk about deduplication ratio for Minerva, we include all the metadata, all the bases and stuff, and compare it to the size of the data we ingest in the system. Where for ZFS, when they report the deduplication ratio, they actually do not provide the size of the scaffolding as a factor in the computation, right? And SDFS actually does the same, but we have ways to identify how much storage space SDFS uses. And you can see here that we have SDFS opt. That is the deduplication ratio. We have SDFS, and that is the deduplication ratio without the scaffolding for SDFS. And then we have SDFS opt, which is with the deduplication ratio, right? And then in conclusion, we have been able to present actually the world's first file system, literally ever, based on generalized deduplication. We have been able to show that we have quite significant gains, up to 63.53%, and only using 20% more storage using gzip. We have only used this achieving Hamming codes, so not the best code for this. We use Hamming codes as the transformation function. And we have been able to achieve this even with this unoptimal transformation function. Additional work is, of course, adding more transformation function, investigating other configurations for generalized deduplication, and also combining MinervaFS with other compression formats, like, for instance, Snappy, and even compare it against Snappy, just raw Snappy, and then add file versioning. So yeah, I finished a bit early, but I'm guessing since there already have been presentations of generalized deduplication, I didn't need to go so much into detail with it.
All right, so very, very efficient. So you compressed quite a bit your presentation, but I hope Mirgita, you're ready for presenting your work.
Okay, hi everyone, I'm Mirgita, I'm a postdoc here at AU. And today I will be talking to you a little bit about the current work that we are doing with some of my colleagues on how we can manage time discrepancy for digital twins. So let's start in the physical world, and this can be many different things, but during this presentation I will use an example from farming. So in our case, the physical world can be a field, and we can have several arable robots on it that will be performing different tasks. This robot that you see here is actually a small sort of iconized version of the Roboti robot from AgroIntelli, which is tasked to do different sorts of operations in the field. So basically we have our setup with a bunch of robots that they are performing their tasks. They might eventually need to communicate with one another if they are within the Wi-Fi range of one another. And eventually they will be able to, and hopefully will be able to successfully perform their tasks. Now, this is what we have in the physical world. And then on the other side, on this sort of little cloud over here, we might want to, on what is the digital world, we might want to do different things. Like, for example, we are interested in monitoring the behavior and the performance of these robots while they are doing whatever they are set out to do. We might be interested to perform maintenance operations without, for example, needing to shut down everything, but sort of doing it on the go. And we might also be interested in doing some supervisory control. Now, clearly, there might be other things that we might be interested in. For example, having some sort of prediction where we have our own models that are running in some simulation scenario, and they are used to sort of predict where the robots should be given certain initial conditions. So what is included here, and more likely even more things, is under this name of a digital twin or a digital replica, which is sort of, as the name suggests, replicating what the robot is doing. What the physical robot is doing. So clearly what we need here is obviously what is needed to realize this. We need to have some sort of exchange of information. So we, of course, rely on data that is coming from the robots, from one or from each one of them. And we also are interested in potentially sending data back, in which could be at the level of supervisory control, reconfiguration, and so on and so forth. Now, a thing here is that the digital twin itself might be at different levels of abstractions. So we can think of the digital twin of a robot. For example, we can think of a digital twin for the whole fleet. The digital twin can be like hierarchical. You could have like one for each robot and then a digital twin of digital twins. So the defining box of what is included, this will depend a bit on what you might be needing. But nevertheless, here, going back to what we see here, so what we find rather interesting in this part where we would like to send different sorts of information, of data, of commands back to the robot. So clearly one question that sort of comes to mind is, are this digital twin and this robot synchronized? So let's concretize this sort of a general scheme a bit further. So we have the real world, which can be the Roboti, this big robot that we saw. It can also be, like Minime, it's a tiny replica, which we actually have here in the lab and we can play with. It can also be obviously a sort of gazebo simulation or of the model of the Roboti, and something that is basically generating data for us, and we can sort of hook it up to what we want to do. Now, on the other side of this, we have the co-simulation world, and the simulation or the digital world, let's say. So this figure here is sort of a representation of the IntoCPS application toolchain. Now, I will not go into details of this, but I will give you sort of a brief intro so that we are on the same page. So let's assume that you have some system that you are interested in simulating and in verifying that it works as you want it to work. Let's further assume that the components that make up the system can be modeled in different modeling tools. So here, for example, in this figure, we can see tools like the Overture, the 20Sim, OpenModelica. And then obviously we cannot just hook this up as they are, right? If we have different components coming from different modeling tools. So in order to do that, we actually need some common interface for that. And this is what the FMI interface is providing. So we are able to define the inputs and outputs of these standardized components that are called FMUs. And then that takes us a step closer to being able to sort of having this jointly execute. Obviously, even with this, it's not enough because they cannot just be hooked up willy-nilly. So we actually need something that is able to oversee or sort of orchestrate the execution of these different components such that it can sort of have them execute coherently in time, such that they can, for example, if I want to go from time 0 to time 1, this orchestration engine over here makes sure that all of the FMUs do this step and is in charge of connecting the inputs and the outputs. So the orchestration engine that we use is the Maestro, which is built by the colleagues here at the department. And to sort of generalize it a bit further, we have the IntoCPS application, which allows us at the higher level to basically describe what are the components that we want to have hooked up in our system and what sort of co-simulation we want to run, and so on and so forth. So going back to this little figure here, we have our co-simulation world, and we can have different things here. So an FMU could basically be maybe some model of the robot which is supposed to predict where the robot is going. And then that might actually help us see, for example, is there any discrepancy between what we are seeing in the simulation and what we are actually seeing the robot doing. Obviously, in order to do this, we need some form of exchanging data between these two worlds, and we have such a component that is packaged as an FMU, obviously, so it will reside in the co-simulation world. So how this works, it's rather straightforward. So our blue arrow, it's our real time, it's what is going on with the robot, that time is progressing as it would. Now, obviously, our digital twin or co-simulation side, that one is sort of dependent on the data that is coming from our real robot. So in order for my system to be able to, for my co-simulation to be able to step, it needs valid data, and then it is able to go to its next simulation step, and so on to go to the next one. So if at any point I don't have any valid data, then I cannot make this jump. Okay, so what can go wrong? So obviously many things, but we are generally focused on two aspects that are related to the network. So we are thinking in terms of the network degradation, and we can think of this as, for example, a 4G degrading to a 2G network, or we could have a temporary network drop, which can be, for example, in case of Wi-Fi connections that can drop and reconnect after some time, potentially. Otherwise, yeah, we wouldn't really know what to do in that case, but assuming that this is sort of coming back. So these are the two kind of issues that we are focused on, and what this means for us and our co-simulation setup, and this time discrepancy that can come up if we are in one of these two situations. So let's look at each of them a bit closely. So here, let's assume, so on my right side, I have my real time that is going, assume that is the clock that is going on for the robot. And here on my left side is the co-simulation time. And I also have like the real time sort of mapped on the side to see how the simulation time actually corresponds to the real time. So let's assume that if I'm in my normal operating conditions, I send a message from the robot, is this green arrow, like brighter green arrow here, and I might or might not have something to send back, but basically, since I'm getting data into my system, my co-simulation side is able to step in time, and it can potentially send or not. This would depend. Then, in case our network degrades somehow, so the messages are coming in at a slower rate, what we can see here is that on the co-simulation side, we are still sort of stuck at step 2, but the real time obviously keeps going. So at any point where we're actually getting this data that allows us to step further, we can actually see that there is this discrepancy between where the real time is and where the co-simulation time is. So, and obviously, if we want to send something back, the same delay probably applies. So we are in sort of this scenario, and we can see this discrepancy. Now, what is acceptable or not, this would sort of depend on what is the tolerance for such time differences. Additionally, you could very well say, but well, of course, on the robot side, we will probably have some sort of mechanisms, not to follow data that is outdated. But that doesn't really help us on the digital twin or on the co-simulation side to be aware of what is going on. So even if we have some sort of mechanism on the robot to ignore such situations from happening, on the co-simulation side, we would actually be blind to it. We have no idea what is going on. So the other issue, or the other thing that can happen, so we might have a network drop, so nothing is coming, so for some time. Then, of course, we are stuck at step 1, and then suddenly the reconnection is reestablished, and we have this burst of messages that are coming in. So here we can actually clearly see that while my system is at my co-simulation is step 1, the real time is at T6. So how can we do this? So obviously the question is, can we actually go from step 1 to step 6 immediately? We can make like this big jump, and then we are clearly able to sort of catch up with the real system. But then obviously this might be a solution, might not be. This depends on whether you would need all these in-between messages or not. So in case you are only reliant on the latest message, then obviously the best thing would be to just skip all the other ones and jump immediately on step 6. So these are our two cases of our network degradation and network drop. So what is then needed? So we need to be notified as soon as possible. So we want to be aware on our digital side, where it's also the smart side, right? We need to be aware that something wrong is going on. We would like to stop sending control data. Obviously, we don't want to just send commands or any sort of information to the robot that can be obsolete. And if possible, we would like to be able to recover from this sort of discrepancy, such that we have the co-simulation and the digital twin once again, the co-simulation and the robot once again aligned. So in order to tackle all of these, we are working on an out-of-sync mitigation component. And what this has, it's FMI compliant. So basically it will reside on the green part of the screen of the figure that I showed before on the co-simulation side. Then beside the FMI interface, it also has a separate way in which it is able to notify a user as soon as something wrong is going on. Well, basically, it's able to sort of notify of this time discrepancy. And then finally, regarding the recovery part, we are working on a Maestro support for mitigation or for recovery. And if you recall the co-orchestration engine that I mentioned before, this is what Maestro is. So it's basically providing support for the kind of setup and tools that we have here in the group. So if I want you to leave with anything from this presentation today, basically, the main point of all of this is that we want to be aware of time discrepancy. And who is we? We is it's the operator, obviously, that might be overseeing what is the actual operation in the field or the operation of the digital twin. But we also want to sort of have this awareness on the digital side, on our digital twin side of what is going on. And clearly, the reason for this is that, first of all, we don't want to send obsolete things back. So that we can, as I mentioned multiple times, I think so that we can try and recover. And so this brings me to a conclusion of this sort of the presentation. So what we call the OSMC, the out-of-sync mitigation component development, is something that is ongoing right now, and I'm working together with my colleagues Casper and Henrik. And we are interested in exploring this in the different case studies. So one of them is the usability with the desktop robotics. So that's the tiny replica that you saw before. And then we are also interested in hooking it up to the AWS server and then representing a bit more of a realistic scenario with actual delays between whatever robot and the cloud. So, sorry. Okay. And of course, this is still not released yet, but we are working on this. If you are sort of interested in looking into it and how it looks like at this early development stage, you can go into that one. And that was all from my side. Thank you.
All right, Mirgita, many thanks for the nice presentation. All right. So Hadi, so it is your turn now. So please go ahead.
So hello everyone, I'm Hadi Sehat. I'm a PhD student at the Genetics group working with Daniel Lucani and Elena Pagnin from Lund University. My main research idea is data deduplication, and today I'm going to talk about a very small IoT testbed that I have set up in home to test what we are researching on. So what I wanted to, the research goal of pretty much my PhD thesis is that we want to have both privacy and compression in a system that uses a cloud storage system. Now for this particular talk, I'm going to talk about sensor data, which still needs to have privacy and compression. Now, if we use traditional methods to ensure privacy and we want to use the data deduplication for our compression tool in the cloud, they have a trade-off with each other, as more privacy means less compression. But with the new idea of total deduplication, we can use compression. We can use compression in order to achieve privacy. I'm not going to overview this because the previous presenters went through this with much more detail than I was going to. But we have data deduplication, which which eliminates the duplicates in the data. Then we have generalized deduplication, which tries to find similarities and remove similar data. And then we have the dual deduplication. The difference between dual deduplication and these two is that in dual deduplication, we not only transform the data in the cloud, but we also do it in the client. And that helps us achieve privacy. A high overview of system model includes a client, an edge, because we have an IoT system here, and a cloud. The client gathers data, sends it to the edge. Edge performs some transformations in order to achieve both compression and privacy, and then sends the cloud to sends the data to the cloud, which compresses and stores the data. Now, for this setup, we used some IoT tools. We used an Spark One sensor, which is an atmospheric sensor to get temperature, humidity, and pressure. We use an ESP32 microcontroller in order to get data from our sensor. And then we use some Raspberry Pi 4 Model B as our edge system, as our edge device. So we put together like this. We have some sensors which gather data and then send the data to our microcontroller. Our microcontroller sends the data to our Raspberry Pi. And in the Raspberry Pi, we process data. Now you might ask, what is this process? And I will get to it in the following slides. And after the processing of the data and performing some transformation, it sends the data to the cloud. Now the process that we talk about in the edge device, which is our Raspberry Pis, is deletion of symbols. As an example, consider that we have a file of, let's say, 10 megabytes, and we delete a chunk of it, say 1 megabyte of it, and then send the remaining 9 megabytes to the cloud. Now this achieves two goals simultaneously. It provides privacy against the big chunk of the file that we send to the cloud, and also reduces data transmission because we of course send less data. And then that 1 megabyte that we deleted will be stored locally. And it can be seen as a kind of base deviation thing that the previous presenters said when they were talking about generalized deduplication. Now in the cloud, we kind of want to use the fact that we are deleting, so we can make this deleting a little more targeted and target specific symbols. And then instead of using traditional duplication on the cloud, we group the symbols in brackets, which can be seen as a kind of binning, and then assign a ID to each bracket and sort the symbols in the outsource file based on their bracket ID. This sorting will allow us to store the bases in a structured data structure, such as a tree or a forest, to improve our duplication search. And by using this, we ensure that we can find the duplication in real time, which is very important for an IoT system. But in order to ensure that we have good deduplication, we need to send a policy from the cloud to the client to make that deletion a little bit more targeted. So this policy will be a probability distribution, which will tell the client to which symbols the cloud wants to see. So the client can delete the symbols that are not very common in the cloud, which will also ensure more privacy because the symbols that are not very common holds more data and provides a little bit more uncertainty to the data. So in order to achieve this, as I didn't have access to the cloud in order to provide privacy and do the sorting thing, I added another Raspberry Pi, which will take care of sort and deduplication technique. So it gets the data from our edge, performs sort and deduplication, and then sends the data to the cloud. And also this Raspberry will provide privacy to our edge device. This is the figure that I took this morning. Sorry for a little bit of being blurry or something, but this is the very small setup that I have at home, which consists of 2 sensors, and you can see 4 Raspberries, but only 2 of them actually work. So in order to get a little bit more technical, I'm using Toit on the microcontrollers, and because they have a very good pub/sub feature, which makes data handling very easy to do. So a big shout out to Toit Group, and they also provided me with the microcontrollers and the sensors. And we also use the Toit Cloud to store data after we do the sort and the duplication. Now, the important thing here is that Toit Cloud itself uses some kind of compression after receiving the data, and we'll see in the next slide how this affects our system. For this experiment, I used a chunk size of 256 bytes, which means the file will be chunked into 256 bytes. And the outsourced size will be 264 bytes. So we delete 10 bytes of data from each chunk. And each symbol is 8 bits or 1 byte. So in other words, we delete 10 symbols and store them locally. And for this experiment, I gathered temperature, humidity, and pressure every 10 seconds. And upload, and the experiment showed that the additional complexity that we add with the sorted application and deletion actually is handleable if we gather the data every 10 seconds, so we can still do that in real-time case. For results, these are the results that we gather after 180 hours of gathering data. If we have no compression, you can see the green line here. Of course, it grows linearly. Now the Toit cloud, as I said, performs some compression. As you can see, it is pretty good by itself. So after 180 hours of data, it shrinks 1.7 megabytes of data into pretty much 300. But if we use our setup prior to sending this to the cloud, we can see even more compression, and we can see that the total amount of required storage after doing our setup and the compression afterwards will be even less than 100 megabyte for a total required storage of 1.7. Now, the big point here is that if you look at the graph at the right side, because we are producing some overhead in the sort and the duplication part, for a very small amount of data, our setup actually reduces the performance in terms of required storage. So I will have less compression because I introduce a little bit of extra overhead. But this overhead helps with finding more deduplications, and in the long run, eventually our setup outperforms when we are not using this method. So this is pretty much it. I think I'm right on time, and thank you for your attention.
Perfect. Many thanks, Hadi. Hope you can hear me. And Zahra is our next speaker. So Zahra, please feel free to share.
Hi everyone, I'm Zahra. I'm a postdoc researcher at Digital Transformation Laboratory, and today I'm going to present my PhD work, which was about secure state estimation for cyber physical systems under sensor attack. First, I will start with an introduction on the topic, and then formulations, and then I will explain about 3 approaches that we proposed in the work, and finally I have a conclusion on my talk. About cyber physical systems, you should be probably familiar with cyber physical systems. As you know, cyber physical systems are the new generation of the systems that provide a tight integration between the cyber and physical sections. Here, we have a schematic of CPS, and as you can see at the top, we have the physical world, and the bottom we have the cyber system, and these 2 components are connected together with using different sensors, actuators, and communication networks. Cyber physical examples are very vast and also are increasing every day. Here you can see some of a few examples of the cyber physical systems, like transportation systems, power generation and distribution systems, and autonomous driving, which all can be examples of cyber physical systems. Cyber physical systems are offering higher stability, robustness, and improved efficiency. But besides these benefits, they have also some challenges, and cybersecurity is one of them. Because we usually connect cyber and physical systems using a communication channel, it increases the risk of cyber attacks. So the reliability of cyber physical systems depends on information technology infrastructures, and 3 fundamental properties of information technology systems are confidentiality, which means data should remain confidential, integrity, which means integrity should be maintained, and information from source to destination shouldn't be subjected to any unauthorized change, and the availability, which means the data should be continuously transmitted. So anything that can disrupt confidentiality, integrity, and availability, we call a cyber attack. Here in this slide, I provided some examples for cyber attack. For example, in figure A, you can see that there is, you can see confidentiality can be violated by a disclosure attack. And you can see that there is no change in the data we receive from a source, but the adversary is listening to the data. And for data integrity, the second type is the data integrity, that as you can see, the data which is received by the controller is manipulated because the adversary injected false data. So for example, if the controller use this fake data, it will be misled. And for the third one is related to availability, and the adversary can interrupt the communication of the data, so the controller doesn't receive any data. Now that we discussed about different kinds of cyber attack, now I focus on the topic of my work, which is state estimation. The state estimation mechanisms are an integral part of cyber physical systems, providing information that can be used for the control, monitoring, and protection of cyber physical systems. The reason we usually use state estimation is that either we don't rely on the measurements or we cannot measure them. So that's why we use state estimation. And but the thing is that state estimation uses the data, and data can be subjected to the cyber attack, and this leads to problems for state estimation. So we have to devise some methods to remove or mitigate the effects of cyber attacks on state estimation. If you go to the literature, you can see there are mainly two categories of articles. The first one is the publication which focus on adversary perspective, which means that they are looking for designing attack scenarios which can bypass the detectors. The goal of these studies is to find the security gaps of cyber physical systems. The second perspective is systems perspective, which can be divided in three categories. The protection-based method, that we try to protect sensors and communication channels. For example, by encryption, we encrypt the data to not allow anyone to read the data. The detection-based methods, they try to detect the cyber attacks. And third method is resilient estimation-based method, which means that the sensors are subjected to the attack, and we try to devise algorithms to mitigate the effects of the attacks, and so we can estimate states correctly. In this slide, let me enable my pointer. I don't know how I can enable my pointer. Yes. Okay. In this slide, I have prepared a problem formulation of my work. And you can see the diagram which visualizes the problem. As you can see, we have a CPS model with input signal U and outputs Y. The data is transmitted by communication channels, and the attacker can compromise the sensors and inject false data to the outputs. So the estimator receives YA instead of Y. So the estimation results might be ruined. So in my PhD work, I have developed approaches to ensure the estimator can estimate the system state securely and remove the undesirable effects of the attack vector on the system state. I have considered some assumptions in my study. First is that the attacker has access to a set of gamma arbitrary unknown sensors, and the sensor set can be fixed or varied over time, which means the attacker can compromise, for example, 2 sensors at one moment, but in the next moment, it can be 5 sensors. So it can change over the time. And we don't know how many sensors are under attack at each time. Second is at any time the attacker is free to corrupt all, some, or none of the compromised sensors. And the attack vector is arbitrary, no boundness assumption, and no statistical attack model we considered for the attack model, which at this point is one of the major and strength points of our research, which we don't assume any assumption on the attack. And no boundness assumption is considered for sensor noise and process noise. And our objectives is to develop a state estimation approaches to securely estimate the cyber physical system state such that the estimation error converges to 0. The first approach that we proposed in the work was a dynamic co-estimation approach, and the contributions for the approach are co-estimation of the CPS states and the attack vector, and concurrent fulfillment of secure dynamic state estimation, attack detection, and attack localization. The state space model of a cyber physical system can be considered as this representation. AT is attack vector, which is added to the system output. If the estimator receives this data, this output value, the estimation error increases, or the estimator might diverge. The idea is to derive the dynamic model of the attack vector, and then we consider the attack vector as a new state, and we augment the dynamic model of the attack vector with dynamic equation of system state. And so we can simultaneously detect and estimate the attack vector and system state. The objectives of this approach are deriving dynamics of the attack vector, and then we need to check feasibility of the obtained model, and then we need to design a dynamic state estimator for estimating the system state and attack vector. To derive the dynamic of the attack, first AAT is considered as an input which is unknown and added to the output equation of system. Then for this system, we design an observer to obtain some initial information about system states. And we obtained the design matrices using with solving a linear matrix inequality problem. Then we obtain output estimation error of the observer. So now using the estimation error and the information we obtain from observer, we can derive a dynamic model for the attack vector. Then we augment the dynamic model with the system model, and we obtain a new state space model for the system. In the new model, attack vector and CPS states are states of the new model. Then we need to check the feasibility of the obtained model. So for that, we need to check the feasibility of system matrices. For example, invertibility of these matrices, and also we need to obtain the statistical characteristics of the proposed of the process noise KAT. For example, you can see here KAT is a new process noise which is related to dynamic model of the attack vector, and we don't have any information about this process noise. So we need to obtain and calculate the statistical characteristics. Finally, we design a Kalman filter based estimator, as you can see here is the formulation of design estimator with covariance matrix P and Kalman gain K. Using the design estimator, we co-estimate the CPS states and attack vector simultaneously and correctly, which means not only we have removed the effects of the attack vector, but also we are estimating the attack vector. We also proved the stability of the proposed method, that due to the limited time, I haven't provided any mathematical analysis and equations here, but at the end of my presentation, I will provide the references for this work. We have tested the method in various scenarios, but I just provided some of them here. The sample CPS which we considered here was an IEEE 14 bus test system, which is a power network system. In this scenario, attacker compromised 4 measurements. The attack is launched at t equals 5 seconds. You can see all the entries of the attack vector are estimated very carefully, and here you can see the system states. The estimation has diverged very slightly at t equals 5 seconds, which the attack is launched, but rapidly it returns back to the real one. I also compared the method with some well-known existing method, and as you can see, the root mean square error for our method is really low compared to the other existing work, and also our method has the ability to estimate the attack vector. In the second approach, we developed the co-estimation method to reach effective filters which can be used to pre-process the data, so we can get a more accurate dynamic for the attack vector. We prepared a framework to design filters, and it gives us several freedom to adjust the response of the filter. So with adjusting and designing the filters, we can obtain information about the attack vector, and then we augment this information with the CPS model, and the contributions of this work are two pre-processing structure are suggested to obtain the cyber attack information, and Kalman filter and two-step Kalman filter algorithms are used to fulfill the co-estimation process, which provide optimal and unbiased minimum variance state estimation. I don't want to go in deep in analysis for designing the process pre-processing structure here, but you can, if you are interested, you can read more in the references. And for the second approaches, we also investigated our method for cyber physical systems which are subjected to the cyber attack as well as unknown inputs. So unknown inputs can potentially represent disturbances, process noises, modeling uncertainties, and so on. So we applied the pre-processed approach to the CPS with unknown input and attack vector, and we derive a new system representation for systems with a new state vector and new design matrices. And in this situation, we will face an unknown input filtering problem, but because we cannot satisfy this rank condition, so we cannot use the two-step Kalman filter, and so we generated some auxiliary outputs for the system, and we add these auxiliary outputs to the system outputs, and then with the new representation of the system, now we can satisfy the rank condition for the system. And for estimating the auxiliary outputs, we used Huygens approximate differentiators. Here you can see the results for the second method. We used an IEEE 14 bus test system. The attack vector comprises two sensors and launches at t equals 10 seconds, and the unknown input is considered as an exponential function. Here, as you can see, we have real and estimated signals for auxiliary outputs, and also in this figure you can see the estimated and real system states. The estimated signal is following the real value, and the estimation error converges to 0. And the final work, I have presented two approaches that I proved analytically that the proposed secure estimators can converge in the presence of cyber attack, but convergence was asymptotic, which means it will take an unknown time for estimator to converge. And the problem that I addressed in the final work, which is published in one of the toppest journal, was that we devised a method which guaranteed that estimation results can converge to the real value in a predefined finite time. Then the CPS is subjected to cyber attack and unknown inputs. Yes, in the conclusion, I just provided my publications which are related to the talk. So for people that are interested in getting to know more about my work, they are more than welcome to read the paper, and yeah, and if they have any questions or comments, I would be very happy to hear from them.
All right, Zahra, many thanks for the talk.
You're welcome.
All right, and I believe it's I'm holding the last slot. So thank you, everyone. Hope everyone can hear me. And in the last item today, right, so I just wanted to give you a quick introduction to this Marie Curie project, European training network that we are running, right? And this is part of this sort of excellence branch in the from the European Commission, right? And the general aim of European training networks is actually to bring very young, early stage sort of researchers in a specific networks with a clear core focus, right? And the IoTalentum one, right? So it's actually, was funded actually in October 2020. So it's been around for a year now. We've experienced some delays, obviously, due to the COVID situation. So we actually have been delayed for about 6 months in our work. But we are at this stage at a point where we've been able to recruit almost all, if not all, of our 15 young researchers to be able to attack various aspects of Internet of Things research, right? And as you can see, it's actually a 4-year kind of initiative, right? So where the goal is not only to carry out research, of course, which the individual teams will do, but also to be able to provide a training activity for all of them. And we've brought together a large, let's say, network of both universities and companies. So anything from, let's say, University of Valladolid and University of Salamanca, right, in Spain, to ISEP, which is in Portugal and Porto, in Portugal. And I believe we have some of the members here, actually. So thank you for joining. We have the University of Eindhoven, Eindhoven University of Technology, sorry. We have, of course, from our team in Aarhus University, Aalborg University is also part of it, from the team that is located in Copenhagen. And we have, of course, members from Simplish Energia, Cryptera, Telefonica, Windtree, and a number of partner organizations, including Mellanox Technologies, which is now NVIDIA. We have Discovery Digital TS and Chocolate Cloud. One of the interesting things about the IoTalentum structure, right, is that we have a number of, not only a project coordinator, but we have a number of mechanisms to make sure that anything from intellectual property to training and recruitment boards are sort of well coordinated by our supervisory boards. And this is, a little bit technical in this sense, but this particular structure in our experience has been working quite well. So I wanted to actually give a big thanks to our project coordinator, Ramon Duran Barroso, and of course our research coordinators and training coordinators of IoTalentum. So they've been very, very critical and very instrumental in making all of this possible. Right? So they've taken quite a bit of work to organize all of the partners and organize the consortium as a whole. At our end, let's say at Aarhus University, we have, let's say, we've been able to hire one of our early stage researchers. So this is his ESR that is here, and he's joined us in September at this point, September 1st, and it's Axel Johansson. I think Axel is joining us today in the call. If you're there, Axel, you can share your camera so that people can see you, if you have a good working camera. And part of the focus that we have is actually on this issue of IoT, but looking at issues of how to do both analytics and privacy with IoT data. And some of the ideas that we have are actually related to some of the concept that you've seen today, right? So looking at how to do compression of the data, how to do analytic with some analytic properties, how to do, let's say, compression of the data with privacy, and ideally what we would like to have, one of the big outcomes that we would like to have from this is actually having this triangle where we are combining analytics, compression, and privacy in a single framework. So that's a big part of what we have. So we do have our own webpage. So if you would like to visit it, it's IoTalentum.eu. So that's something that is available. And just to give you a little bit of a sense of how we've organized the network, it has three main focus work package, right? So, and one of them is particularly focused on infrastructure, network, and computer resources. The other part is obviously related to cybersecurity. And finally, we have some level of applications with a big, let's say, focus on smart grids. And in that sense, right, so if we look at the infrastructure research objectives, this is one of the places where Aarhus University is taking a key role, right? And clearly, we are looking at sort of mechanisms that allow to do this, bring together these ideas of privacy, compression, and analytics, and provide key supporting technologies for both the edge and the cloud. And this is particularly important in this context, and we are going to start working more actively now that we have hired all of the students with this different partners here. And one of the interesting things is that as part of the network, we have a lot of segments. So the students will actually be visiting the different partners for periods of 6 months at a time in many cases. So we have, of course, some stronger focus, let's say, in more traditional cybersecurity and cryptography, and that's part of where Cryptera, which is a company here in Denmark, University of Salamanca, Eindhoven, and Aalborg, and of course Digital will take a big part of. And for the applications, we actually have a number of providers and focus on energy, of course. And we also have universities with a specific focus on smart grids. As I said, we have around 15 early career researchers or early stage researchers. And at this point, we have, I believe, if not all 15, I think 14 already sort of have started at this point. So we are ramping up our research programs. And we have all of the ESRs actually enrolled in PhD programs in the different universities. And at least one of the things that we do is that we have sort of a split of the different students in secondments, and at least they spend 6 months in any individual partner, but we try to make sure that they have 10 months of secondments, and a large part of that actually in industrial partners to give them more support for their activities and ground them in not only in theory, but also have a grounding in very practical considerations. I just wanted to give you a little bit of a very, very quick overlook of how some of the training activities or training program we have looks like, right? And I'm not going to go into the details of the specific subjects that we cover, but I can point out some of the, let's say, partners that are more or less involved in some of the educations, right? And what we see is that in some of the aspects that have to do with networks, for example, we have definitely involvement from Mellanox. Aspects that have to do sort of that work at the interface of networking and computing, right? So we have variation from University of Valladolid and a number of our industrial partners as well. When we're looking at security and computing, some of the courses will actually be covered in part by members from Aalborg University and of course of one of our industrial partners, Chocolate Cloud. And interfaces between security and networks, right? So all of those different angles are actually covered by some of the universities and companies at this stage. So we have this sort of core thematic, let's say, activities, right, grounded on some of the technical aspects. But of course, we have sort of as well a key focus on various applications, right? So in particular, smart grids, and obviously some more, let's say, cross-cutting activities for the training program. So if you wanted to go a little bit deeper, right? So we have sort of some elective and compulsory ECTS, and of course we do have something grounded on scientific and technical topics. But we have, as I mentioned before, but we have some aspects or some training for transferable skills, right? And this has to do, and never mind the C7, C8, C18, that's our internal codes. But we do have ECTS that have a focus on ethics, academic integrity, open science, gender balance, and diversity in general. We have some other aspects that are focused on entrepreneurship. So we want to have the ability to provide additional let's say, skills to the different ESRs. And of course, there will be some training on dissemination and communication. And we are planning to have a number of summer schools to be able to bring all of the different ESRs together to be able to have, let's say, joint experiences and be able to exchange let's say, to have a common, let's say, training activity, as well as being able to share with one another their experience in their PhD research, and of course their experience and their, let's say, advances in their own PhD work. Finally, there's of course a number of other, let's say, activities, but there's definitely a strong support that tries to, cover a lot of the different requirements of different universities, but also making sure that we provide the best training and education to the different ESRs, aside from their research experiences in both academia and industry. So in name of everyone in IoTalentum, I just wanted to give you many thanks for allowing me to present this. And hopefully, if you have questions or if you have some interest in this, please feel free to contact me, and I will, let's say, definitely point you in the right direction. All right. If you have, of course, questions about research and collaboration, particularly in these topics, please feel free to drop me an email. I'm happy to connect you to the right speakers, right? And you can, of course, if you want to contact them directly, that's also very much allowed. If you are, if you're watching this and you find this to be very interesting and you would like to present your work at future events, please drop a line to Litte. So she's our person in charge of making sure that we have good quality speakers in every session. The final point is actually that we have an upcoming event next month in November 24th. I'm not going to be organizing it in this time. We actually have, and he's sharing his video. So we have actually Alexandros Yosifidis, which is one of the associate professors at our Department of Electrical and Computing Engineering. And he is leading a number of efforts in machine learning at our faculty, right? And maybe, Alexandros, you can introduce yourself and just give very quick overview and maybe a vision for the next.
Yes, thank you, Daniel. Yeah. So next week, next month, we will present the work of my group. We are very active in machine learning, deep learning, artificial intelligence, methodologies for computer vision, fintech, and other interdisciplinary research topics. So we will present work that is done in 3 European projects and a couple of national projects. Computer vision, robot vision, financial time series analysis, credit card fraud detection, and other similar topics. So you can check the website of Live from Behind the Walls, and you can see the list of the presentations for the next month seminar.
All right, and I should say registration is open for that event already, I believe, Litte. So we encourage you all to register and to talk to your friends and colleagues and check this out. And I know that Alexandros is doing very exciting research, so I encourage you all to participate in that case. So thank you everyone for staying until the end, and thank you to the speakers for giving their presentations, and many thanks for keeping all of them sort of